Hello, my name is Bilal and I'll be speaking for my group for Part B of the Turtlebot 3 Simulation and Control coursework. The first two tasks we were asked to do were based entirely in simulation, giving us the chance to explore the principles of robot control in a safe, idealized environment. The final two tasks then transitioned that knowledge onto the real robot, allowing us to prove that our setup, communication, and hardware were functioning correctly. I will begin with Task 1, launching the Turtlebot 3 burger in the gazebo simulator and controlling it through keyboard teleoperation. The purpose of this task is to build foundational familiarity with the toolchain we use throughout the coursework, namely ROS nodes, topics, and simulation in gazebo. We first configure the Turtlebot 3 model type, then open the simulation environment, which loads to a realistic physics engine, a model of the Turtlebot, and the sensors mounted on it. Using a separate terminal, we launch the teleoperation node, which allows us to send commands directly from our keyboard to the robot's motion controller. These commands are sent as velocity messages, and we can immediately see their effect on the robot's movement inside the virtual world. Even though there is no video of our own for this task for now, the expected behavior is that the robot should translate and rotate smoothly as we navigate around the environment. This demonstrates the essential communication pathway between user input, ROS messages, and robot action, a key interface that carries through every other task we perform. Task 2 expands this simulation by incorporating SLAM, which stands for Simultaneous Localization and Mapping. The challenge here is that a robot operating in an unknown environment must build a map of its surroundings while continuously estimating its own position on that map. In this task, we run a SLAM package, specifically G-mapping, which uses the onboard LiDAR sensor and odometry data to generate a two-dimensional occupancy grid. As the robot moves through the space, we would expect to see a map gradually form in RViz. Areas observed by the laser appear as free or occupied, depending on whether the beam's encountering open space or walls and obstacles. Meanwhile, the robot's pose estimate becomes more accurate as more of the environment is explored. The outcome of this task, even though we were unable to record a video, is a complete representation of the virtual room once we have driven around all the boundaries. It also helps illustrate why proper exploration matters. Without steering the robot into every corner, gaps will remain in the map. These first two tasks are intended to show how robot motion, sensing, and perception integrate before we ever move into the real world. This brings us to Task 3, where we finally power up the physical Turtlebot 3 burger. Here, the focus shifts from theoretical expectations to verifying that the hardware and software are correctly configured. The robot's onboard computer, a Raspberry Pi 4, runs the ROS master, which coordinates all communication between nodes. We start by connecting to the robot over a network connection using SSH, allowing us to operate it remotely through the command line. Once logged in, we launch the Bring Up package responsible for activating all essential systems: motor drivers, the LiDAR scanner, the IMU, and other embedded controllers. During this step, we monitored data streams to ensure everything worked properly. For example, we used ROS tools to check that the LiDAR was sending scan data at the correct rate and that wheel motion was responding accurately to commands. If something did not respond, this stage gave us the opportunity to troubleshoot wiring, firmware installation, or incorrect configuration settings. Successfully completing this task confirmed that the robot was fully functional in a standalone configuration. Finally, Task 4 required us to network the Turtlebot 3 with a remote PC and perform teleoperation over Wi-Fi. Both the robot and the PC must share the same wireless network, and we configured their ROS environment variables so that they communicate with one another seamlessly. In our setup, the Turtlebot 3 serves as the ROS master, and the remote computer connects as a client machine. Once we confirmed that the devices could reach each other on the network, which is something we tested using pings and reviewing ROS topic lists, we launched the familiar teleoperation node from the PC instead of the Raspberry Pi. Immediately, we could see the real Turtlebot respond to our keyboard input, driving forward, reversing, and rotating based on remote commands. This proved that the control, perception, and localization were all functioning over a distributed system. To conclude, this coursework allowed us to transition smoothly from simulated learning to real robotic operation. We began inside Gazebo, exploring movement and sensing in a virtual world. We then expanded our understanding through SLAM, where mapping and localization occur together. From there, we successfully powered, tested and verified the physical Turtlebot 3 hardware. And finally, we established full wireless communication between the robot and the remote PC, demonstrating real-time teleoperation and sensor streaming. Overall, the progression of these tasks helped build confidence in both the software infrastructure and physical system behavior of the Turtlebot 3 platform, allowing us to experience firsthand how theoretical robotic principles translate into practical implementation. Thank you for listening.